The radio telescopes will be driven very rapidly, eventually scanning each patch of the sky 30 times. But it is in frequencies sampled rather than directions covered that NASA's project will dwarf all previous searches. Drake's lone frequency is gossamer thin in comparison to the tens of billions of usable frequencies in the naturally quiet microwave window. And even though the Ohio State Survey covers lots of directions and stars, about 60% of the sky overall, its frequency range is also limited. META also scans the northern skies, but all of its 8.4 million channels cluster around a single magic frequency, though it will be tuned to others. In contrast, on the frequency dimension, NASA's Sky Survey will cover the whole 1 to 10 gigahertz window and the entire sky. To achieve this comprehensive coverage of directions and stars, NASA plans to use several telescopes around the world, which are part of its spacecraft tracking system. Each of these telescopes can see 2/3 of the sky, and NASA will move its Sky Survey system between them.
The complementary approach is to say, let's concentrate on detecting with more sensitivity, be able to detect weaker signals, and to do that we look in a few directions for longer periods of time, and that's called the targeted search. And we pre-select a set of stars that we know a priori are more or less similar to our own sun in age and size, and look in those directions with more sensitivity and the ability to detect maybe more complex signals.
The targeted search will look repeatedly and at different frequencies at nearly 800 nearby stars. Like Nancy, NASA's targeted search may start around 1420 megahertz, that is 1.42 gigahertz, but then it will expand to cover all frequencies between 1 and 3 gigahertz. Like the Sky Survey, the targeted search requires antennas around the world. The giant radio telescope at Arecibo is the largest on the planet, and because of its unique size and sensitivity, NASA hopes to share time to search for the very faintest signals. The large dish can't be moved, so it can only see stars which rotate overhead each day. The antennas at either Ohio State or Nancy could be used to observe about 300 stars outside the range of Arecibo. More of the target stars can be seen from the southern hemisphere, so about 200 of them could be observed from the large NASA antenna at Canberra, or perhaps the astronomical facility at Parkes in Australia. The last 50 or so stars must be searched from a telescope in the northern latitudes, perhaps, rather appropriately, from Green Bank, where Frank Drake began the search with Project Ozma. With this unparalleled combination of advanced hardware and sophisticated software, NASA's project will have the capability to revolutionize SETI. The targeted search will look for faint signals from what, according to the current understanding of cosmic evolution, seem to be the most interesting sights, and will look at billions of frequencies. The Sky Survey will cover an even wider range of frequencies, yet with sufficient sensitivity to detect a very strong signal from clear across the galaxy. In addition, NASA's system will have an unprecedented ability to look for different types of signals that vary over time. Not just a continuous carrier wave like that of Pioneer 10 or Earth's radio broadcasts. For the first time, we will be able to detect regular pulses that some researchers say will save energy and so be the choice of a transmitting civilization.
The interesting thing about the SETI search is that although we claim that we're looking for extraterrestrial intelligence, we can't actually define what an intelligent signal is. And so a starting point is to say we look for a signal which nature will not produce by any mechanism that we understand.
Kent Cullers helped NASA design the smart computer algorithms needed to locate weak signals in the many channels of noise. But there will be no human staring at sophisticated graphics displays. No human is any more sighted than Kent when it comes to recognizing an extraterrestrial signal.
So the eye is not a good detector, first of all, in sensitivity. A thing that you could look at virtually forever and you would never know whether you were seeing random noise or whether you were seeing a real signal. The computer can find signals that are 10 times weaker than that. The amount of data processed per second is the equivalent of the entire Encyclopedia Britannica per second. Now, of course, that's filled with random letters, if that's analogous to noise. And what you have to do is find that one pattern that says, "Hi there," in all of those random letters that come in every second, and then decide whether that pattern could have happened at random because of your statistics of your process, or whether, in fact, that's the real thing. And a human being, even if he could perform the task as effectively as a computer, couldn't do it for very long.
Removing humans from the signal detection process requires very special hardware, which is what Ivan Linscott and his colleagues at Stanford University have been designing.
And that's like having 10 million ears, each one listening to a particular tone, and where all of those are listening simultaneously. And so what we're doing now is taking the technology that exists in this prototype form and casting it in sand. And we're building silicon versions of our processors that together with the way we know how to use them will condense both the scale and increase the performance.
The process of miniaturization is already underway. 680 of the older large boards will soon be replaced by just 24 smaller boards, filled with new chips that are cheaper, smarter, and faster, and can be more easily transported around the world.
It no longer will require you to step in small chunks across the frequency band. You can make giant strides and spend lots of time on particular sources or sweep broad swaths of the sky. And I think there's where the opportunity lies, because it's a prospector's art, and you just have to look and take your best bet.